Do it like this. So, okay, so welcome back to the reinforcement learning lecture. We will continue today our discussion about variational inference and its connection to control. And where we have been stuck at the last lecture on Friday was basically discussing different divergences that we could use for approximating distributions. And we had this discussion about the Kullback-Leibler divergence. And one was the forward Kullback-Leibler divergence, and the other one, the reverse Kullback-Leibler divergence. And so here we see the equations. We see, okay, Kullback-Leibler divergence is not symmetric. So it makes a difference how you put it, the order of the arguments. And so we had these two different divergences. One was called as the reverse, which we also called information projection, because it tries to keep as much information from the target distribution in the approximated distribution. And information, we know it's a well-defined term in information theory. It's basically minus the log probability of an event. And what we can see if we look at this equation here, so we had the argument, okay, that this is zero forcing, right? Or we called it zero forcing, because if you look at the equation here, whenever this P star, which is the target distribution, is very small, it's close to zero, the only way to get this Kyle down is to set P to zero as well. Because otherwise the divergence will be very high. So it's rather hard to optimize the eye projection. So it's a non-convex optimization problem. So we'll see for the other projection, for the moment projection is convex. It's much easier. But you have the advantage actually that you don't need samples from P, from this P star. You only need to know P star, or up to a normalization constant. So you basically need to know this P star tilde, which is the unnormalized density. And that's usually, when we talk about intractable distributions, we usually only know this part. We don't know the normalizer, because it's very hard to compute. So we don't know this set here, but we don't need to know for the eye projection, so that it doesn't bother us. And also, as a recap, what was the basic property coming out of the zero forcing argument is that that the eye projection is a mode-seeking divergence, or a mode-seeking minimization, which means now if you have a target distribution that has several modes, and you want to approximate it with a distribution that has less modes, so for example, a Gaussian only has one mode, then the information projection will pick one of the modes. Because what it cannot do is to go between modes, because there will be a very small target density, and we set it zero forcing. It needs to be zero there. And this reverse KL is actually the KL we are interested in when we talk about variational inference. Because actually of this property that it doesn't put probability mass of the approximated distribution somewhere where is actually no probability mass of the target distribution. So for sampling, for generating samples, this is a good thing, because the samples you generate, they're all valid samples. It could be that you leave out some of the probability space because you ignored some of the modes, but the samples you generate, they should be good samples that if you use the eye projection. So The moment projection is just the KL the other way around. It's a forward KL. It's called moment projection. And I think that's more or less where we stopped discussing why it's called the moment projection. So we'll continue from there. Yeah. The moment projection, I mean, there's now a lot of red stuff that I scribbled on it, but what you can basically see, first of all, is that for the moment projection, you need samples from your distribution, because this is an expectation of, with respect to the target distribution of log QX. And you can, usually you approximate expectations by samples from this distribution. The second observation, and that's actually, I think, quite interesting, is that this moment projection is something we did all the time. It's just the maximum likelihood estimate. And that's basically, if you look at this integral here, where basically this part here is part of the constant. It doesn't depend. So the px log px doesn't depend on q, so you don't need to consider it, isn't it? You optimize for q. And if you look at the expectation, you can basically use the standard thing that we always did, say, okay, we can estimate the expectation by Monte Carlo simulation, plug in our samples from P star of x, and then it looks like the sum over our samples log q of xi, and that's maximum likelihood. What we have here is still a minimization problem, but the minimization of the negative log likelihood. And this is something that we do that is a standard thing to do in supervised learning. If you have a probabilistic model, you would use minimize the negative log likelihood to find the parameters of the probabilistic model. So that the forward KL is basically an old friend. We already know it. Maybe we didn't know that we know it. But the basic property of the forward KL is that it is a probability forcing. We can see that also on the equation here is basically whenever this P star is high, also the log Q of X needs to be high. Because if log Q of, if the Q of the Q of X needs to be high, because if Q of X is close to 0, the log would be minus infinity, and because of the minus in front, that would be very high. So we wouldn't want that, because we minimize. So it's probability forcing, which means everywhere P star is high, Q needs to be high. But it doesn't really care about the regions where P star is close to 0, isn't it? If you look at the objective, everything is multiplied with P star. If this is close to 0, who cares? And from that, you basically see what it would do is, if you have a bimodal distribution, the blue one, you want to approximate it with the Gaussian, you would put the Gaussian in the middle. And basically, that's exactly what the maximum likelihood estimate does of a Gaussian, isn't it? If you have samples over here, you have samples over there, you put it in the middle. So far, so good. Any questions? Okay. I mean, and I think that's basically where we stopped the last time. So, and then there is also an interesting additional observation. Why is it called the moment projection? It has also nothing really to do with variational inference right now, but I think it's interesting observations to understand in general what is going on in machine learning. So we just covered here because it fits quite good if you discuss this divergences. So why is it called the moment projection? So what you can do is basically for exponential family distributions, which are it's a very general class of distributions, isn't it? So most distributions are from the exponential family. A few are not, but most of them are. Gaussian is definitely. And the exponential family distributions, you can parameterize them like this. So it's an exponent of some features of x times some parameters divided by the normalizer. The Gaussian, for example, looks like that. How would the features of the Gaussian look like? Feature vector? So if you remember, how does the Gaussian distribution look like? It depends on the mean and the yes, but these are the parameters. So this would be mean and variance would be part of theta. But what the Gaussian distribution looks like is we have basically inside the exponent, isn't it? We have the x minus mu. Okay, minus mu. Let's keep it simple, just in the scale minus 1/2. This is inside the exponent, isn't it? Of the Gaussian distribution. And which is the quadratic function, isn't it? And the key is just, okay, we can write this also as some features of x times theta, isn't it? Depending a little bit how we define theta. So we could now, for example, say the phi of x. And here, basically, we need to include every nonlinear term of x that is composed in that is part of our equation that we have. So every nonlinear term of x, or every, yeah. So what would that be? Is x part of this equation? Minus, yeah. So what you would get out exactly, so what you would say is you would compute this, look at the square, isn't it, in the bracket. So what you would get out is minus x squared, then plus 2x mu minus mu squared divided by 2 sigma squared, isn't it? So that's what you would get out. Yeah. So maybe we can do it now. How could I write this equation here as a phi of x times theta? Yeah. Yeah. I mean, I think the one even we could forget about it. It's just part of the normalizer, but we could write it, yes. Yeah. Look at that guy. Yeah. Okay. So um. So let's forget about this one for now. Yeah, we are only interested in terms that depend on x. So theta would be minus 1/2 variance, isn't it? So that's the factor that is in front of the squared pi. And for it would be mu times mu divided by sigma squared. And what we typically do to write it a little bit simpler is that we wouldn't put the minus 1/2 here, we would put the minus 1/2 here. So we can still do that. This PowerPoint, I hate it. Yeah. And then basically we covered all the terms that depend on x, isn't it? And there we can directly see already what theta is. Theta is 1 over. Theta is 1 over the variance and the mean divided by the variance. And these are so-called the natural parameters of the Gaussian distribution. The precision and mean divided by mean times precision. And precision is the inverse variance. The natural parameters. And why are they called natural parameters? Because they are the parameters that make the Gaussian density log linear in the parameters. If you log it, it's just linear. So the Gaussian distribution would be a case of that, but many other distributions are exponential family. And we can write it like this. Does that make sense? Oh. Okay, so let's have a look what we can do with it. So if we now plug this structure in of the exponential family, exponential of features times theta, into our log likelihood estimate, then what we get, or in the log likelihood, is just the sum of my samples of the log of q of x, and I want to optimize the log likelihood, isn't it? So I compute the derivative of it. And if I do that, I get the following equation. The green sum and the blue part, the green sum is basically the derivative of the x of the features times the parameters. So the log and the x just cancelled, isn't it? Minus n times the normalizer, because the normalizer is there every time, isn't it? And the log is basically causing this minus. N times the log normalizer. And the normalizer here is just this integral again. Otherwise, it wouldn't be normalizing the distribution. Okay. So if you look at it again from at the next at the next line, so we have the sum over the features, because here this derivative just theta goes. So this the sum over the features of my samples, sum I phi of xi. minus. And now the question is how easy that is to understand. But so who can see how to go from here to here? Although there are quite a few steps at the same time, so maybe let's try to do the steps step by step. Right? So the derivative of a log of some function, what is that? Or know the function. So we have the log of some function, and the function is of theta. So it's a function that depends on theta, isn't it? This is that 1 over z times the inner derivative. And the inner derivative is the derivative of the integral x of phi of x times theta. The integral remains, isn't it? Because every term in this integral depends on theta. So the integral here remains. What happens to x of phi of x times theta if I compute the derivative of that? Yeah. Exactly, and that's what we have here, isn't it? But it's just okay. Chain rule. We have to apply the chain rule several times. And okay, now you can say, okay, that's a little bit calculus. I don't care. But what comes out is the interesting result. So we see now we computed the gradient, and an optimality condition for theta would be the gradient equals 0, isn't it? So then we know we are at an optimal solution if the gradient is 0. So basically, if this one is 0. And we also see, okay, the sum over my features, that's like a feature average, isn't it? Times n. It's just, we didn't divide by n, but it's like a feature average in my data. And the second equation here is actually also surprisingly simple. Because what we see here is nothing more than the expected features of Q. Because x per phi of x times theta divided by z, that is exactly Q, isn't it? That's how we define it. So the Q falls out of this equation again. And then it's the integral of Q of x phi of x, which is the expectation of Q of x phi of x, of phi of x. And what we have here is that and we can basically just forget about the n, isn't it? So if you want to set it to 0, we can just cancel the n. That the average feature counts of my samples need to be the same as the expected features, or the average feature counts of my samples from P need to be the same as expected features from Q. And that's why it's called the moment projection, because this expectation over some features with respect to a distribution, these are called the moments. So if phi of x equals x, it's the first moment. If phi of x equals x squared, it's the second moment, and so on. And basically, the optimality condition is these features need to match. You need to match the features of your data, the feature averages of your data. You need to match the moments. And that's exactly what we do when computing mean and variance of a Gaussian distribution, of the samples of a Gaussian distribution. We are matching the first and second order moments. nothing more than that. And that's a convex optimization problem. It's very easy to solve. But I think, yeah, has been now a little journey into distribution matching, but I think it's a quite interesting insight to see that. Any questions? No. Okay. Then here maybe just again to see again the properties of both protections, so the information protection on the left and the moment protection on the right. And as a summary, the information protection has the advantage that we don't need to know the normalizer of P star. It's mode seeking, so we only focus on one mode. It's a good generative model because the samples that we would generate are all basically in spaces where G also has high probability. But it's hard to optimize even for simple Qs. So even for a Gaussian distribution, which is the most simple thing we know in continuous spaces, isn't it? There is no closed form solution, and we have to do some non-convex optimization. Which makes sense just looking at the picture that there is not one unique solution as well. So like this one is a valid solution, but putting the mode here a little bit nicer than I did is also a valid solution. Both of them are equally good. So it cannot be convex. So, and yeah, on the moment protection, it's much easier to optimize. For most distributions, very, very easy. It covers all area of high probability, but it requires samples from P star. If we do maximum likelihood, then we have it. That's exactly the setup. If we do variational inference, we don't have samples, but we have P star. Have to remember that. Okay. And what we will now do is basically to see how this framework matches or can be applied to reinforcement learning and optimal control. And you can also maybe already intuitively see which one do you think is better for reinforcement learning? Which one of these formulations? If you, for example, now would think, okay, the blue lines here in this plot here are not my log, not the density of the target distribution. Maybe it's a reward. It's a reward function. Then I would argue this one is better because we find one solution where the reward is high. We don't care about the other solution. In comparison to this one, where we would try to cover both solutions where the reward is high, but we are somewhere in the middle where it could be arbitrary. So again, in reinforcement learning, we also want to have a distribution, which is a policy that generates good samples, isn't it? And that's exactly the case on the left. Okay. I think this slide, yeah, this should be not there. Yeah, and we can quickly discuss it. Because we can also already see a relation between reinforcement learning and variational inference if we look at the equation. So variational inference, we had the Q of x log P star of x plus the term that is missing here, or let me write this differently. So it's a q of x log q of x minus q of x log p star of x. That's the same thing. And in variational inference, we said it's a minimization problem. I can always turn a minimization problem into a maximization problem, isn't it? I can just multiply everything with -1, then it looks like that. And here I can already say, okay, maybe that looks somewhat similar to a reinforcement learning problem, or a very simple one. I mean, there's only x. Let's say x are not the actions. But I could not say this is the reward. The log p star of x is the reward of x. And this term here is also something we already know. Who can recognize this term? Yeah. It's entropy of Q, exactly. So this is the entropy of Q. And talking about entropies and reinforcement learning, which formulation was that? So we talked about maximum entropy reinforcement learning. Well, we didn't cover it very much, but this was a soft actor critic algorithm, was an instance of maximum entropy reinforcement learning. They basically just said, we want to maximize reward, but at the same time, we want to keep the entropy high. And so forget about this episode-based setting that will come later. But in this simplified setting where we only have x and there are no states or something like that, so x are the actions, it would basically, the maximum entropy reinforcement learning would look like that: qx, rx, want to maximize that, plus some alpha times the entropy. And now we see already this looks somehow similar, isn't it? So here maybe we don't have the alpha here. This is the only thing that is different. But in the end, also that doesn't really matter, because the reward, I can arbitrarily define the reward, isn't it? So I can now just divide everything by alpha. So I can move this in here, so Rx divided by alpha. And then I just have this equation here. So, and basically from that we can see that variational inference is defining actually, or is solving the same problem as maximum entropy reinforcement learning, where the reward is log p star and alpha equals 1. And vice versa, maximum entropy reinforcement learning is just solving a variational inference problem. Where the target distribution, p star of x, is given by the exponential of the reward divided by alpha. And that's why we can directly transfer these properties that we just discussed, the mode seeking property of the error projection, directly to reinforcement learning. Yeah. And what definitely both statements, problem statements, have in common is that they have to optimize over sampling distribution to generate their own data. So the task is to get a good sampling distribution with high target densities or high rewards, high log target densities or high rewards. Okay. So the question is now, how could I optimize, for example, such an equation with respect to Q? Which kind of methods do we already know to do that? looking back at our lectures, which algorithms did we do to optimize distributions so far? And with distributions, I mean policies. So probably Q-learning is not the right answer here, isn't it? Because, yeah, policy gradient algorithms, yes, exactly. Yeah. Policy gradient algorithm is an algorithm to optimize the density. It doesn't matter whether it's a policy or something else, isn't it? It's to optimize the density. Policy gradient. Then was the second one? Yeah. Yes, which, but in actor critic, we use the specific algorithm to optimize the distribution. So in soft actor critic, we use that, for example. You still remember? If we reparameterize, the reparameterization trick. These are the two instances that you can use to optimize densities, either policy gradient or reparameterization. When do you use what? So that's what we discussed basically at one of the recaps where we did this small example with the Gaussian distribution, isn't it? So policy gradient, I typically use it if I don't know R, but I can evaluate R. So I can basically ask the function R, what is the value? I can do that. But for example, I don't know the structure of R. I cannot compute derivatives or something like that. And the reparameterization trick, there I have to know R because I need to know the derivatives. But if I know the derivatives, the reparameterization trick was much more efficient because you get better gradient estimates with less variance. So, and that's basically the different ways of dealing with it. From the algorithmic side, you can use likelihood ratio policy gradient, like the reinforced algorithm to do that. Yeah, it's called black box variational inference. And black box, why is it called black box? Because we don't assume we know R, the structure of R. R is a black box for us. We can just ask R, what is the reward? The black box variational inference. The reparameterization trick, and we could do something more fancy than standard policy gradient. We could do natural gradients, for example, with the trust region. And there are different algorithms or that use different approximations of the of Q. So, for example, you could use the so-called mean field approximation, which we have here. Gaussian distribution with a diagonal covariance matrix. What is usually better is the full covariance approximation, but it's harder to do because much more parameters. And what is working the best usually, but even harder, is a Gaussian mixture model approximation. Gaussian mixture models, yeah, I think most of us should also know that from some other lecture, probably Grundlagen der KI, or in machine learning, we discussed that. It's really just a sum of multiple Gaussians. So the Gaussian mixture model. So what can a Gaussian mixture model do what a Gaussian cannot do? Yeah, multi-modes. Yeah, exactly. And so that Gaussian mixture model can do this. And that's why it's in many cases better. Right? Okay. So let's see that we now go back to our original problem, which was reinforcement learning and control, and see how this fits with variational inference. So, because why do we want to use control as, or formulate control as inference? Especially if you want to talk about modeling human behavior or behavior also in animals, the optimal control is not a very good mathematical formulation of that, because you rarely see a human acting optimal. There is always noise on our actions. I will never be able to execute a thing in the same way. So, and some mistakes do matter more than others, and that's what a human is optimizing for, So if you could not say, okay, there's always noise and there's nothing we can do, isn't it? That would still be part of the Markov decision process. But what a human basically does is, if the error I do in following a trajectory doesn't matter, then I don't care. So I only get a small reward punishment, I don't care. If I would get a high reward punishment, I would care. But the optimal control theory would say, oh, you have to care about the small reward punishment as well. And there's only one optimal solution for this. But our behavior is inherently stochastic. So we will always do this going to a target point, for example, in different ways. But so if the task is going to the target point, we will go there in different ways, but we will all reach the target point. So for this point where it matters, we have accurate control. So, and that's basically can be much better described by inference, because it can also model suboptimal behavior. And there is a huge literature of different inference algorithms that we could use if we can formulate optimal control or reinforcement learning as inference problem. So, for example, there are planning and state estimation algorithms like Kalman filtering, or so that could just use that also for optimal control. Yeah, and it also provides an explanation why sometimes stochastic behavior is preferable. For example, in exploration or in transfer learning, this is the case. Okay, so the question is now, how can we formulate inference as a control as an inference problem? And so what you can see here on the right is a graphical model. Who knows what a graphical model is? No one, yeah. Yeah, we definitely need a lecture discussing that a little bit more, but I think in Grundlagenarchie we do it in 1/2 lecture. Probably you guys were still the Coxis guys. So, but a graphical model, we don't really have to understand much here. We see the graphical model here on the right. It just indicates all our random variables that we have, and the dependencies of these random variables. So the arrows indicate the dependencies. So S2 depends on S1 and A1. Yes. In addition, we have one more variable here, which we call the optimality event. It's basically a little bit artificially defined. It's an event of being optimal, binary. You're either optimal or not. And you also see that this is gray, isn't it? And the other ones are not gray. And it's also means something slightly different. So it means that this random variable is observed. Basically, assuming that we see the optimality event every time step, so we are optimal at every time step, we want to know the state and action distribution. This is the inference problem. Huh? The probability distribution of state and action given that we are optimal. Huh? And we can define all of these distributions very similarly as in a Markov decision process. We can define the trajectory distribution. That's what we already know. Now, we don't use a policy here because we want to infer the policy, isn't it? We want to know the policy. So the policy is just a uniform policy. So we would take every action with the same probability. That's a prior policy. We could put a more informative prior here. But for now, we will just use this. And then we can define an optimality event for every time step. And that's what we have here. And it's again a very similar trick as we have seen before to discuss how reinforcement learning and variational inference are connected. We just say this optimality event is proportional to the exponential of the reward. And then we can similarly say the optimality event of the whole trajectory, which basically means we want to have at every time step we want to be optimal. So that would be just the product of the P of small ot equals 1 given st and at. And because the product of exponentials, you can basically say that's the exponential of the sum of the arguments, isn't it? So it's exponential of the sum of the rewards along a trajectory. So I have now basically a distribution for the trajectories, a prior distribution because I use a prior policy, the uniform one. Yeah. I have so a likelihood of optimality and what I want to have is the distribution of trajectories given I am optimal. How would I compute that in inference? If I have these two, how do I get to that? Yes, the Bayes rule is 50% always the correct answer. Yes, so, yes, of course, Bayes rule. The Bayes rule can be used to reverse probability, conditional probabilities, isn't it? And that's what you see here. Yeah, so I can use the Bayes rule to have the prior trajectory distribution, the blue one, times the probability that the trajectory is optimal, which is the likelihood, divided by the normalizer. This guy is again hard to compute. This guy's here. But for us now, it's sufficient to know that this posterior probability of trajectories given optimality is proportional to the prior times so optimality likelihood. Yeah. And then if we have formalized it in this way, we know now basically the target distribution, which is the posterior of trajectories conditioned on being optimal, having a little bit this fake optimality event. And I can apply variational inference. So, and for doing that, I can say, okay, I have, so maybe one more thing to say. So I want to have this posterior, isn't it? But I cannot compute the posterior because of this guy. I don't know that. Normalizer. But I already said a couple of times, we can apply variational inference no matter what, whether we know the normalizer or not, isn't it? We don't care. The eye protection doesn't depend on the normalizer. So that's basically the key idea. How can we apply variational inference to the control problem? We now use again a variational distribution, Q of tau. This is the distribution we want to use to approximate the posterior. And it will be factorized as follows. It's again the initial state distribution times the transitions times Q theta of A given S, which is in this case a learnable, trainable policy. And then we can basically do the standard thing that we did before, which is minimizing the eye projection between Q and the posterior. Which is again equations, but in principle, you again see that we have the normalizer here. This one disappears in the constant, and what remains is basically the Q of tau log of the probability of being optimal given tau. And we have a second term in there, which is basically Q of tau log P of tau Q theta of tau. So these are basically these blue parts, and you can basically see this is again actually a KL between your variational distribution Q and the prior P. So what we want to get is basically the distribution Q that optimizes my rewards, or this log optimality condition, which we'll see is just a reward, but at the same time is close to the prior. So both objectives. And if you plug that in, and you see again, a lot of mass, but you actually see most of these things cancel out, and it's actually not so complicated as it looks in the beginning. So what we need to plug in is basically just for the second part, for this KL part, we plug in the structure of these distributions. Where we said, okay, the trajectory distribution is the probability of the initial state times the probability of each transition times the policy. And for P, we said it's a uniform policy, so it would be there, but it's just one, it's just a constant in this matter. And so that's basically what we have here. We set in our factorizations for the trajectory distributions. And the log of the optimality event given the trajectory is just the sum of the rewards divided by alpha. That's just how we defined it. And then you basically see that even though the equation looks terribly complex, it's not, because everything here cancels out, isn't it? Except for this guy. So what remains is the log of the product of Q of A given S, and log of the product is going into a sum of the logs, isn't it? That's the standard thing to do. And this sum is basically going from here to here. That's what we see here. So when we apply variational inference on computing on approximating the posterior distribution of the optimal trajectory distribution. It's optimal trajectory distribution, I mean this condition on the optimality event. Then it is actually the following optimization problem. I want to find a trajectory distribution that first of all optimizes the return, sum of the rewards, and at the same time optimizes or has this minus log Q in there. But if we analyze that a little bit more, this minus log Q this is contained in the entropy of the distribution, isn't it? The entropy was integral over minus Q log Q. And what we basically can do from the last line here to the next line is to write this expectation a little bit more explicitly, not in terms of the trajectories, but in terms of the states and actions for every time step. That's what we have here, the expectation of a state and actions for every time step, where the expectation is done with respect to the state distribution at time step t. And the state distribution follows from the policy and the policy. And then we basically see, okay, we want to have a policy that maximizes the reward, but at the same time maximizes the entropy, because we have basically Q log Q from this part here to get the entropy. And basically that's how people show the equivalence between max entropy reinforcement learning and variational inference. Because what we see here is exactly the same objective that SAC is optimizing, for example. The soft actor critic algorithm. Optimize rewards. So the soft actor critic algorithm has the Q function in there, which is basically a proxy for the rewards, for the long-term rewards, plus plus the entropy of the policy. And yeah, long story short, I mean, a lot of math, you don't need to know this math by heart, obviously, also not for the exam, but what you should know is basically max entropy reinforcement learning and variational inference is essentially the same thing, also for the sequential case when we talk about trajectories. For the single time step case where we only have actions, it's quite easy to see that. That was the slide like three slides before. For the trajectories, it's not so easy to see. You need all these derivations. If you don't want to remember them, forget about it, but just that you have seen them once. How you would go there, yeah? And it's a lot of basically always, okay, you have logs of products that you can turn into sum of logs and something like that. This kind of tricks. Questions? No. Okay. Yeah. I know it's a lot of math, and our brains are cooking, I think, right now. And that's something that has to settle a little bit. The main important thing is basically, yeah, this here. Huh? Okay, but what does it mean? So we said, okay, soft actor critic is solving a variational inference problem. And that's why soft actor critic works so well. Because if it wouldn't do that, it would just optimize the policy without the entropy. The policy would very easily collapse variance and wouldn't explore anymore. And you get stuck. That was the story why we need the entropy. So if you look at the objective of SAC, it is this one, yeah. So we want to optimize for a policy that has a high Q value, high expected Q value, minus log of the density of the policy. We basically know this is the entropy of the policy. And now we can interpret it in this way that we say, okay, this is an a projection problem, a variational inference problem, where we want to know the policy pi. We have a target distribution p star, which is the exponential of q divided by alpha. And having a look at the right side, basically, where it's visualized how it would look like. So for example, if the q function looks like this, so we have the actions here on the x-axis. This is now for a constant state, just for the same state. The q function would look like that. So it is quite good here. So it has the optimal solution. Here it also has a good solution, but it's not that good as the other one. Then the target distribution would be the green one. Exponential of q, and an exponential of q looks like the green one. Obviously, it cannot get negative. But whenever q is negative or very low, target distribution is close to 0. So whenever q is higher, the target distribution is also higher. And now the variational inference problem is to fit the Gaussian distribution on this target distribution. One solution would be the red one, in this case, the best solution. Another solution would be we could put it here. Or we could maybe use a Gaussian mixture model to represent both solutions. That would also be interesting. Okay. Good. Yeah, so this slide is basically just the wrap up. So how could we now do that? Formalize control as inference problem. We introduced this binary optimality condition. Am either optimal or not? With the probability of x of the rewards. Then I said, okay, I can define it as an inference problem by computing the posterior distribution. But I cannot compute this posterior distribution because of that bad guy. But what I can do is I can use variational inference to approximate the posterior distribution. And if I do that, I do it's the same as max and reinforcement learning. And I mean, I also told you, okay, the max and reinforcement learning is used for SAC. That's one of the most famous algorithms, but actually many other algorithms also use it. So like the PPO algorithm that we got to know, we didn't mention it, but one of the many hacks and hyperparameters is in there to add the entropy with a certain factor. So it's also doing max and. Because it just helps for the exploration. Okay. And yeah, the next 20 minutes, let's see whether this is enough. We will also have a look at variational inference methods for latent verbal models. So that's also not directly connected to reinforcement learning, but we will need it later for other reinforcement learning models that use latent verbal models. Who of you guys know what a latent verbal model is? Yes. Yes. What is the latent variable? Okay, that's maybe already 3 steps to 5. Yeah, but that's maybe how you would apply it then. Yeah. But what exactly is a latent variable? A latent variable is a variable that we don't observe. So an unobserved variable. So usually when we talk about maximum likelihood of a probability distribution, all the variables are observed. And then we can just maximize the likelihood of it. Latent variables don't have this property. You don't know them. And for latent variable models, there is an algorithm called variational base. That's a standard algorithm to use. And that's a variational inference algorithm. And latent variable models, now it sounds very abstract, but it's a huge class of algorithms, variational autoencoders, which is like probably, I don't know, 20% of machine learning algorithms are using that. That's exactly where we would use variational base. So, and now we have already a lot of knowledge in variational inference, so it makes sense to look at this algorithm also and try to understand it. So, because the latent variable models are actually the main application to variational inference. So the examples would be variational autoencoders, the mixture models, missing data, latent factors, dimensionality reduction. For all these things, you can use variational inference and latent variable models. And as we already said, okay, so what is a latent variable model? It's a model where we have two sets of variables, observed ones and unobserved ones. X observed, Z unobserved. So we still have a distribution over both. So we have a distribution B of Z and a B of X given Z. And this distribution we want to know given data. But the data is only X because Z is unobserved. And now, if we don't know Z, we cannot optimize the likelihood of it, isn't it? It's unobserved. Yeah. But what we can do is we can optimize the likelihood of X, of the marginal distribution of X, P of X. And this is we know how to compute marginal distributions, isn't it? So we just integrate out the unobserved one. Either using a sum in discrete spaces or integral in continuous spaces. And what we said is, okay, we have data, we have multiple samples of X. We want to optimize the likelihood, log likelihood optimization, marginal. In this case, it's called the marginal log likelihood because it's just in X, not in Z. And we see that basically we need to optimize the log of an integral, which we can maybe still approximate by the log of a sum. But we would need a lot of samples here to approximate as well. And we can already see that here, so it's a sum over many, many different latent variables sampled from the prior distribution. And then we basically want to optimize the log of b of x given this sample set. And we would need to do that for every x, for every sample x that we see. We need many different sets, many m's to approximate this integral. So, and computationally, that this is just not doable because for every data sample you have, you would need, I don't know, 100 or 1,000 set samples. And it's very, very hard to do that. It's just too slow. And why is this, or maybe in another view of that, why this is not a good idea? So by looking exactly at the structure of the log sum structure. So for example, let's say we have prior distribution in Z. It looks like this. But now for a specific xi, the likelihood the b of xi given Z maybe looks like that. It's very peaky at a certain position. Because it basically means a certain xi has been generated by a certain latent variable. And if I would do it like this, I just sample from the prior, I would generate many, many samples here where this b of x given Z is basically 0. And it doesn't contribute to this sum. But I need to be very lucky to get the sample here. And then this one sample changes everything. So we can already see that such an estimator, it's a valid estimator, but it has a huge variance. And in order to fight huge variance, it always means you need very, very, very many samples. So the standard maximum likelihood is not a good solution for such a latent variable model. Yeah, and forget about this one. So we need something better. And this is what variational base is doing. So this is again throwing a lot of equations at you. But let's try to understand what variational base is doing. Variational base uses the lower bound of the marginal likelihood. And it optimizes the lower bound instead of directly the marginal likelihood. Why is this a good idea? Because the lower bound is easier to optimize, or it doesn't have this variance, this huge variance. And for simplicity, we will only look at the single data point right now. So before we had here the sum over my data points. Let's do it only for a single data point. So I have only the log b of x of one data point. And then the lower bound looks the following. I have the term here on the right and the second term. And so what we can see, the term on the left and the second term. Let's look first at the second term. Yeah, the second term is q of z, log q of z, divided by b of z given x. And that's something we already know because it's a Kullback-Leibler divergence between q of z and b of z given x. And now, maybe you might ask, what is this q of z now? We haven't seen that before. It's a new distribution we introduced. Yeah, the distribution that is there to approximate the distribution to approximate basically the distribution b of z given x. Yeah? And so this is basically on the right side. We will see on the next slide why this lower bound is valid. How to come to this lower bound, we will need a long time to figure it out, and it's not obvious. Yeah, but you can show that it's valid, and then maybe you also see a little bit how to come to this lower bound. Right? But for now, let's just believe it is like that. We can always say log p of x, the marginal likelihood, is lower bound than the Kullback-Leibler divergence, and this lower bound is valid for any q. It doesn't matter. Q just needs to be a distribution. It's always valid. So maybe one question. I now say this is the lower bound, the left side here. Can you already see why it is a lower bound? Yeah. So if this part is always larger equals 0, then this part can only be smaller or equal this part, isn't it? So it's always a lower bound. Okay, so we introduced now a new distribution q of z. Okay, you might ask now why, but we'll see that this distribution q of z makes the optimization easier. And why is it the same thing? That should come on the next slide. Yeah, but in principle, what you can also quite easily verify, if for this distribution, the posterior distribution b of z given x, we just set in base rule, we will see that everything cancels out and just the log b of x remains. So it is really always the same. And yeah, one side note, and that's the people that have been sitting through the machine learning lecture might know that. So also expectation maximization, which is a very famous and widely used machine learning algorithm, is the same principles, the same mathematical principles, using the same lower bound. Just expectation maximization has one more simplification assumption that we will discuss a little bit later. But okay, so we have lower bound plus Keil divergence. So how do we get there? As you know, there are some mathematicians that are sitting in the corner and thinking about nasty tricks, how to transform equations, and this is also the case. How they did that. So the nasty tricks is basically to don't change the equation, but try it more complex manner. So the first part, the log p of x is the integral of q of x log p of x. Yes. Because the integral of q of z is just 1, isn't it? then what I can say is for the B of x, I can use Bayes' theorem, which is written here. And now you would say, this is not Bayes' theorem. What are you telling me? But it's an awkward version of Bayes' theorem. Standard Bayes' theorem would be B of z given x equals the B of x given z times B of z divided by B of x. But this is the version of Bayes' theorem that you know, isn't it? And now I can just say, I multiply with B of x and I divide by B of z given x. So I just exchange these two guys. And then I get here. So this also holds always, isn't it? B of x is B of x given z divided by B of z times B of z divided by B of z given x. And I can just take this and plug it in to get to this equation. Integral q of z log B of x given z B of z minus log B of z given x. And then I can again think of another nasty trick. I can add 0. Well, minus log q of z plus log q of z. Didn't do anything, isn't it? And if I do that, then I get the first part here, the lower bound, and the second part, including this q of z, the cat. And we did nothing more than integrating over a distribution that is 1 and plugging in Bayes' theorem and adding 0. But how to get there, it's another way of magic. But now we can at least verify that this is the case. Yeah, does that make sense? So at least you can verify the steps, and we just believe it is like that now. We can confirm it. Lower bound plus Cal. And what I already said is the variational inference, it optimizes the lower bound instead of the log likelihood. Why is it the lower bound? We already discussed that because the KL is always larger or equal to 0. It's also quite often called the evidence lower bound, the elbow, very common term for all this literature, because the marginal log likelihood is also often called the evidence. It's lower bound to the evidence. Yeah, and what variational Bayes does now is it looks at this lower bound, and the lower bound depends now on Q, on this new distribution that we introduced, and on P. And it optimizes the lower bound with respect to P and Q at the same time. But what we have won now, so you can again see, it's again a complex equation, so why should I do this instead? But we have won something very substantial. The integral is outside the log instead of inside the log. We moved it outside, the integral over z. And that makes a lot of things easier, because if you have a loss function that is just an expectation, we know we can optimize this loss function using stochastic gradient descent, no problem. But if you have a loss function that is some nonlinear stuff of an expectation, this is not possible with stochastic gradient descent anymore. So you would need a lot of samples to approximate this expectation, right? So basically optimizing the loss function to the lower bound is much easier because you can just do stochastic gradient descent and even just use one sample of Z, one sample of X. You can do it. And yeah, the variational base algorithm, so it basically now optimizes different sets of parameters, so Q, P, and the prior of the latent variable. And so if you formalize it like that, so you can also show, because we optimize the lower bound will always go up. It's not guaranteed that the likelihood will always go up. We need one more condition for doing that. People sitting in the machine learning lecture will maybe remember for expectation maximization, the likelihood is always going up. For variational base, it is not. Because variational base has not the assumption that the posterior, this one, can be computed exactly, which is the assumption in expectation maximization. That doesn't matter for now. But exactly this formulation is a standard for basically all latent, continuous latent variable models. The variational autoencoder is an instance of it. And I think that's a good closing point for the day. Tomorrow there will be the exercise presentation again, but I think we have now 3 or 4 more slides to discuss here. We'll also finish that tomorrow to finish up this lecture and do some more practical examples. And that's it for tomorrow. And then for the next 2 weeks, then Rudy will take over and do some other exciting topics. So thanks for coming and looking forward for tomorrow.